The condition that a rigid body is rolling without slipping on an inclined plane is. Here we have to check the options one by one. Let us start with the first option. It is acceleration less than g. Consider an inclined plane at an angle theta with horizontal, and there is a body which is just rolling down this inclined plane. As we know, acceleration down the inclined plane for a rolling body is g sine theta divided by 1 plus k square by r square, where k is the radius of gyration and r is the radius of the rolling body. For any value of theta less than 90 degree, we can say this acceleration will be less than g. But for any body which is not rolling down, simply coming down the inclined plane, its acceleration will be g sine theta. Here also for theta less than 90 degree, acceleration will be less than g. So here we cannot generalize that for a rolling body only the acceleration down the inclined plane will be less than g. So the first option is not correct. If we go for the second option, it is rotational and translational kinetic energy to be equal. We know the expression for translational kinetic energy is half mv square, and expression for rotational kinetic energy is half I omega square, where I is the moment of inertia. For a ring, we can write the moment of inertia is mr square, and omega square can be replaced as v square by r square for rolling. Now this r square will be cancelled out and we will be getting half mv square as the rotational kinetic energy. Here we can see the expression for translational as well as rotational kinetic energies are equal. So for a ring only, these two kinetic energies are equal. So we cannot generalize that for any rigid body or any body rolling down the inclined plane will have a rotational and translational kinetic energies equal. So the option B is also not correct. Let us check the third option. It has linear velocity equal to radius times angular velocity. As the body is rolling down a fixed inclined plane, the point of contact should be addressed. For this, at point of contact, VCM is in forward direction or down the incline, and R omega in backward direction. These two should be equal for the point of contact to be addressed. So VCM should be equal to R omega is true. So we can say the third option is correct. Let us check the fourth option also. It is saying that the plane is frictionless. Here we can say if the plane is frictionless, there will be no torque acting on the body. If there is no torque, the angular speed will be not increasing with respect to time. If the angular speed is not increasing, every moment VCM cannot be balanced with R omega as VCM is increasing due to mg sin theta. So we can say without friction, this body cannot roll down the inclined plane. So fourth option is not correct.